Welcome back. This is lecture 3 of Computational Neuroscience, Systems 552, Biology 487, taught at the University of Waterloo in winter 2021. This lecture we are covering perceptrons. What's that? Well, okay, so back to this overall diagram that we're going to be using throughout the course. We're basically going to be starting looking at the very first computational models of neurons and very, very small networks of neurons. Okay, so, and we do have some optional readings. They're both sort of old the classic papers that sort of started this whole field, and so they're listed as optional readings mostly because they're sort of there for historical interest and sort of seeing how people were talking about things at that time. A lot of the notation and things like that has changed a lot, but as you'll be finding out throughout the lectures, some of the core ideas are just exactly the same as what people are thinking about right now. So it's interesting to go back and see where it all comes from. All right, so we want to make some sort of artificial neural network. We want to have something that looks like neurons do something. And neurons are ridiculously complicated. What matters? Where are we going to start? What's the simplest approximation of a neuron that we can start with? And once we've got those simplest approximations of neurons, how are we going to get them to do anything useful? Okay, so let's start right at the beginning. This is McCulloch and Pitts, 1943. This is one of the optional readings. And here's the particular set of simplifications that they decided to go with. So they just, all right, so number one, we're just going to consider that the neuron is either, it's an all or none process. It's either outputting a 1 or it's outputting a 0. I will note that this isn't necessarily spiking, so it's not like if I give it a, so because it's an all or none process, that means that if I give it like a constant input that's enough to make the neuron active, then that means the neuron's activity sort of stays at 1 and just stays there all the time. It's not that it is spiking over and over and over again. It's not like spiking up to 1, back to 0, up to 1, back to 0. The activity of the neuron is just sort of stays at a 1. The idea that they're doing there is they're sort of like, okay, even with a real neuron, if it's spiking at some rate, if we sort of like just sort of look over a window of time, then is there activity or is there not activity? And that's really all they're sort of saying. Okay, that's their first assumption. We're not going to worry about how fast it's firing. It's just, is it firing or is it not firing? And then what we're going to say is, well, what causes a neuron to fire? A certain fixed number of synapses must be excited within some period of time in order to excite the neuron at any particular time. And they're going to say that this number is independent of any previous activity and where these connections are on the neuron. So what's that saying? That's just saying, okay, every neuron has a bunch of inputs, and if in one time step enough of those inputs are 1, then my neuron will have an output of 1. The only significant delay within the nervous system is the synaptic delay. So that's saying, okay, the only thing we're worrying about is it takes time for one neuron spikes and that communicates to the next neuron, or one neuron produces an output that's going to communicate to the next neuron. We're just going to call that one time step and just say, all right, whatever my neuron does right now is just dependent on the inputs from the last time step. So far, all of those input connections that have been talking about right now have been excitatory. Have been all the inputs just sort of make things make the neuron more likely to fire, or not more likely, but if enough excitatory inputs are active, are set to a 1, then the neuron will fire. But then the exception is there's also inhibitory connections. Again, this is something you see in biology. There's some neurotransmitters that cause current flow into the cell that makes it more likely to fire, and there's other neurotransmitters that cause current to flow the other way and makes the neuron less likely to fire. So we're also going to include inhibitory connections, so connections that make the neuron not fire. And in fact, we're just going to make this an absolute thing. It's like even if there's 100 excitatory synapses and 1 inhibitory synapse, that inhibitory synapse is going to stop the neuron from firing. And we're going to say that we're not going to adjust this network at all. We're just going to build the network, and there's no learning rules that are adjusting these weights in any way or adjusting these connections in any way. So that's their attempt at a minimal version of how we can build things with neurons. So what can you do with that? They started sort of playing around with, okay, what can you do with things like that? And they made these sorts of diagrams here. So the way that we're showing what these diagrams are is these weird triangle things. That's the neuron. These lines, the line coming off to the right of the neuron is the axon. And then you get these solid dots. Those are excitatory connections. And the number is just saying this is neuron 1 and this is neuron 2, just so you can refer to the neurons. And for all of these particular diagrams, a neuron requires 2 excitatory inputs to be on in order for that neuron to be on. Okay. So what you've got in this first diagram is a system where, all right, if this neuron here is on, if neuron 1, maybe this neuron 1 is some sort of sensory neuron, it's some sort of input neuron. So I'm controlling the input to this neuron 1. If neuron 1 is active, then that's going to have 2 connections to neuron 2. And so that's going to be enough to make neuron 2 active. And so if neuron 1 is active on the first time step, then neuron 2 will be active on the next time step. And vice versa. So this is just sort of, you could call this a communication channel, or it's just a wire. Neuron 2 will do whatever neuron 1 was doing, but there will be a one-time step delay because of this this communication here. Fine. What's this one over here doing? Well, neuron 1 and neuron 3, that's about the same thing as before, but now we've got neuron 2 connected to this neuron. And so now neuron 3 will only be active if either 1 or 2 are active. Right? If I activate neuron 1, neuron 3 will be active. If I activate neuron 2, neuron 3 will be active. If I activate both neuron 1 and 2, neuron 3 will be active. You can think of this as an OR gate. Right? This is taking, neuron 3 will be active if neuron 1 or neuron 2 is active. Similarly down here, let's see if I've got this sort of setup where I've got only one connection from neuron 1 to 3 and one connection from neuron 2 to 3. Well, now this is an AND gate. This neuron 3 will only be active if both neuron 1 and neuron 2 are active. Okay, so you're starting to maybe see how we can start building something up out of neurons that can do things. Final example, do this one over here. We're showing an example of an inhibitory connection. So if neuron 2 is active, then that will stop neuron 3 from being active. And so that means neuron 3 will only be active if neuron 1 is active and neuron 2 is not active. All right, so you can start getting these sorts of NOR type operations. And that sort of logic, in this paper, they sort of lay out a mechanism for taking any sort of logic expression and turning it into a complicated network that'll do whatever you want. This is a sort of read the paper if you want to know what this particular thing does. But those are the sorts of diagrams that they sort of build up. And in the process of doing this paper ends up being, well, first of all, it's the first paper that sort of lays out, hey, you can build things with artificial neural networks. So it sort of establishes artificial neural networks as a field. As a side effect, it also is the sort of the foundational paper for finite state machines and cellular regular expressions, finite automata, that whole side, which some people may be familiar with. The normal paper that's cited that sort of starts that field is this one here. 1956, or at least sort of a more common one. It's got some. I mean, this is pretty much beside the point of the paper, but I love these sorts of comments in that paper. They say that, oh yes, this present article is partly an exposition of their results, referring to the McCulloch and Pitts. But we found that part of their paper, the one that was dealing with arbitrary nerve nets, neural networks, arbitrary neural networks. We found that obscure, so we've proceeded independently from there. We've ignored their results, and we're going to do it our own way because we couldn't figure out what the heck they were saying. There's other sort of snide comments in there, like, well, this apparent counterexample discouraged us from further attempting to decipher part 3 of McCulloch and Pitts 43. These sorts of back and forth, like, I cannot imagine writing a paper with that sort of sarcastic comment in it, but it's amazing to sort of see that at that time. In any case, foundational paper, how do you build things up out of basic neural networks? But relatively limited and mostly focused on, yes, you can hand design these things. And if you've got some sort of logical circuit and you want to convert it into some sort of network, yes, it's possible to do so. At the same time that finite state machine paper, same year the finite state machine paper came out, there's also this paper, which introduces the perceptron, which is sort of the main topic of this lecture. Rosenblatt, 1956. And here's sort of the core idea of I want more complicated functionality out of my system, and how am I going to get that without all of this really careful hand designing of these complicated networks? And here's the core idea. The core idea, first of all, okay, you've got some sensory data coming in. The particular thing they're imagining here is vision. So this is just light coming in, and you've got some sort of retina, you've got some sort of bunch of things that are sensitive to light. And then what you do is so these things will be active if light is falling on them, okay, only on their particular pixel. And then what you do is you've got this other group of neurons over here, this what they call the association system, or whatever. We'll just call it another group of neurons. So these are going to be our inputs over here. We've got a bunch of neurons here. And what we're going to do is we're just going to randomly connect these inputs to these neurons. So what's that going to mean? That's going to mean that each of these individual neurons here is sensitive to some random or some arbitrary combination of the raw input image. So we're going to have a whole bunch of neurons here that are sensitive to something. And then, okay, so each of these individual neurons is pretty useless. Like, what can you do with that? Well, here's what we're going to do. What we're going to do is we're going to add a response unit. What this is going to be is something that's going to take input from a bunch of the neurons from this layer. It's going to do some calculation on that and produce an output. Okay. And the idea is going to be that if you adjust these connection weights, so if these sorts of the amount of connection, so these response unit here are going to be something like add up all of these inputs. They're going to do, and if we adjust these connection weights here, then we can adjust what this response unit is doing, which means we can adjust what this whole system is doing. And what we should be able to do is do something like, I don't know, do an image recognition thing. So I don't know, if you show a picture of a cat here, I want this output to be 1, and if we show a picture that's not a cat, then I want the output to be 0. And the idea is you should be able to do that just by adjusting these values. All right, let's talk about that in a little bit more detail. This is a slightly different diagram with that same idea. Input image, and I guess in this particular case, instead of recognizing cats and pictures of cats, this is recognizing the letter X. We have this layer of things that are extracting some sort of features from this raw data. We have raw data coming in. I have a bunch of things that are extracting some sort of features from that raw data. That's the same on this diagram. That's these neurons here that are sort of randomly connected to my input. From each of these outputs, so each of these outputs is going to be measuring something. This is my set of features, which is why it's, in this particular book, Minsky and Papert perceptrons, which I'll talk more about as we get there. They're using the symbol, the letter phi for that. Anyway, whatever. We've got these sorts of features are coming in. We're going to do something to those features to produce an output. And the particular thing that we're going to do, let's be a little bit more specific than do something. The idea with a perceptron is, hey, all we're going to do is we're going to take these individual features, we're going to multiply each feature by some number, we're going to add it up, we're then going to compare that, we're going to subtract some other value, and that's going to produce our output. And our output is just going to be, hey, we do all this math, and if that turns out to be greater, if this sum is greater than theta, or if this sum minus theta is greater than 0, then our output is 1, otherwise our output is 0. That's the standard classic perceptron model. You can see it's kind of similar to what the McCulloch and Pitts is doing. The new additions is instead of just 1s and 0s, we have these weights. But this, does the total. If we'd set all the weights to 1, then this would be exactly the same as the McCulloch and Pitts idea. Because this bias, or this theta here, is the, well, how many inputs have to be active in order for this neuron to be active. So that's the original construction of this. This is a little bit more common now. The way we might write this now is we might generalize this a little bit and say, all right, we've got some input. We're going to do some sort of weights on those inputs. We're going to add up all of those results. And that'll get the how much activity is coming into the neuron. And then there's going to be some nonlinearity. And that's going to produce our output. Okay. So really the only difference here is the original classic perceptron, it was always this sort of harsh, either output a 1 or a 0. It's become a little bit more common to have some sort of other function there as well. Apparently I have a diagram of that. So here's the, we can think of this is the original perceptron function. Artificial neural networks have often gone with other functions. This is a particularly common one, the sigmoid. We will talk about that later. And that used to be the thing that everyone used, but there's now something else that everyone uses. We'll get to that. One other tiny little difference that is going to come up, well, it's sort of more of an implementation detail. Technically, the perceptron should be written this way. This whole sort of, okay, I've got a bunch of inputs. We've got a bunch of features being extracted from whatever my input is. That's X. Each of those features can be multiplied by some weight, and that's all going to be added up. And then we're going to subtract out the value that says, okay, I need a number bigger than this in order to fire. Just to simplify the math, a lot of times this will get reorganized to say, all right, we're just going to say you're just adding up the weights of a bunch of features, but it just so happens that there's one feature that is always set to 1, and we're going to have a weight on that feature that is minus theta. Right? And so if you do that, these two equations are exactly the same. Right? If you just, instead of this sum being from 1 to n, the sum goes from 0 to n now. So you've just added a new feature. That feature is always 1, and this weight thing here is your theta value. Okay. So that transformation is just sort of something that is so common for artificial neural network people to do that it's almost just assumed that everyone always does that. So there tends to be this extra feature that is just always 1, and that's how we get our bias. That's how we get our, what will this neuron do in the absence of any other input? Or if I want the neuron to fire more readily, then I'll just increase this weight. Right. If I want the neuron to fire less readily, I'll decrease this weight. All right, makes some sense. That's at least sort of the basic math. We can again see that you can build the same sorts of AND gates, OR gates, things like that. And indeed, these diagrams are almost become exactly the same thing as what were shown in the McCulloch and Pitts situation. If I have a weight of 1 on this and a weight of 1 on this, and then I have my bias weight is minus 1.5, then that's going to mean that this neuron is only going to fire if my input, suppose my inputs were either 0 or 1, then this neuron is only going to fire if this input is a 1, if this first input is a 1 and the second input is a 1, because that's the only way. 1 plus 1 is 2, minus 1.5 is still a positive number. I will get an output of 1. So that would be my AND gate. This over here would be an OR gate. If either of these two is active, then my output will be active. You can also, if you have a negative weight here, now you can do an inversion operation. So this will be active if and only if the input is not active, and so on and so forth. So again, you can build the same sorts of things with perceptrons as you could with these McCulloch and Pitts neurons. But there's a little bit more that we can play around with, because we've added this idea that we've now gotten to this domain where these inputs can be, we can also start imagining the inputs are continuous values. They don't have to just be zeros and ones. And we have these weights that we can adjust. And one way you can imagine what these weights are doing is these are sort of, if we plot the space of our feature values, so we've got these two feature inputs, we've got x1 and x2 as our two features. And if we want a system that only outputs a 1 when both of my features are 1, and outputs a 0 when in all other conditions, and if we allow inputs that are either 0 or 1, sorry to get to that in a moment, then one way we can think about what we're doing when we set the weights of our connections here, when we set this bias weight and we set our weights of our connections, it turns out that what we're really doing there is we're drawing a line in this space, and everything on one side of this line, the output is 0, and everything on the other side of the line, the output is 1. And as we adjust the weights, as we adjust these weights, we're sort of rotating that line. And as we adjust this weight, we're sort of shifting that line. So you can sort of see that the line is as we go from this diagram to this diagram, the line is shifted down. Okay. That starts giving us an intuition as to what this system is going to do if we started putting in values that weren't 0 and 1. Oh, hey, look, if I put in a value that's 0.5, this system is going to output a 1. Whereas if I put in 0.5 over here, this system over here is going to output a 0. Makes some sense. It's just another way of depicting the math that's being shown here. Of course, this opens a little bit of a question of, oh, well, what do we want to do in this situation? What if we wanted to output a 1 if either of those features was a 1, but not both and not neither? And we'll get back to that in a bit. We'll get back to how we can deal with that problem in a bit. But the core idea here is if shift adjusting those weights, all that's doing is drawing a line in my feature space. So this feature space is, so now we're in a domain where our inputs can be not just 0 and 1, but anything we want, any sort of continuous value. The limitation on the perceptron is that we're always going to be having some line, and it's going to say 0 for one half of this line, or for one side of this line, and 1 for the other side of this line. And that means we can't compute things. So if we can't do something like, oh, I want this system to output a 0 if feature 2 is sort of in a middle range of values and feature 1 is also in a middle range of values, but if either of those are anywhere outside of the middle range, then I want the system to output a 0. Okay, and this is sort of saying that no, you can't mathematically, there is no way of setting the weights to make that work. And that was actually a really important thing that they were doing when they were researching things. They really wanted mathematical proofs and mathematical ways of analytically sort of describing what these systems can do. So there was a lot of attention to trying to describe what systems can do. Especially, and as a big part of that, there was also, fine, okay, there's limitations on what these lines can do, but there's also this question, where do we get these weights? Because I don't want to like hand pick, that was the whole thing with the McCulloch and Pitts systems, is you were sort of hand designing all these weights. You can go build up what you want, or is there an alternative? And the idea is going to be that we're going to start with random weights, and then we're going to adjust the weights to improve performance. And we're going to improve performance based on, hey, it's going to produce some sort of output. We can check whether or not that output is right or not, and if it's wrong, we can go and change something. Right? So another term for that that's often called that supervised learning. It's a situation where we're doing learning where whenever we get something wrong, we know what the right answer should have been, so we can train it. Okay. So how the heck are we going to do that? Well, we're only going to change we're doing this by changing weights. Fine. If the output's correct, then don't change your weights. All right, that's easy. So we're only going to change our weights if the output's wrong. Now, if it's wrong, then I got two options. Either the output's too low or the output's too high. If the output's too low, then we want to increase our weights. If the output's too high, we want to decrease our weights. But like, well, which weights? And if I want, but the effect of these weights, each of these weights, it's getting multiplied by the activity or by the value of that feature. So let's adjust the weights based on the current value of that feature. So what do I mean by that? So the weight for the ith feature, so I don't know, feature 1. So there's one particular feature I'm thinking I've got right now. What I want, and let's say that feature has a I don't know, say as a feature has a value of 0.7. Y desired minus Y. So Y is the actual output of the system. Y desired is what the output should be. If Y desired equals Y, so if the output is correct, then that's 0. We're not going to change our weights. If Y desired minus Y is positive, that means that my value is too low. I'm going to multiply that by my value for my feature. That kind of makes sense because any feature that's 0 right now, that weight isn't being used, so we shouldn't be adjusting that weight. So Y desired minus Y, we're going to multiply that by the feature, by how active the feature is right now, and then we're going to put in some learning rate parameter. So how much, so I don't know, 0.1 or 0.01, some value that says, okay, I'm only going to adjust the weight a little bit. But that's my idea. I'm just going to take how much I'm wrong by, multiply it by the value of the feature right now. That's going to tell me how much to change my weight. That's the core Perceptron learning algorithm. And if we run that, so here's going to be an example of running that. Here's my data. I've got a bunch of data that is, and for the red dots, we're supposed to, so I've got two features, that's on the x-axis and the y-axis. For the red dots, the value, the network is supposed to output a 1 for that. If the green dots, the network is supposed to output a 0 for that. And all we're going to do, all we're doing here, is we're just each time the graph is updating, we're just grabbing one of those points at random. We're seeing what the network does to that point. If the network's doing something wrong, then we apply that connection weight changing algorithm, and we continue. Okay. So let's try that again. Oh, and the line is that line I was saying that you can take a set of weights and turn it into a line and say, okay, well, given that set of weights, it's always going to output a 1 for things on one side of this line and a 0 for things on the other side of this line. So it's sort of a quick way of knowing what the network would do right now. And you can see that it very quickly, after even just sampling a few points, starts being becoming a line that does a good, that sort of, all right, separates the red dots from the green dots as much as is possible. There's some overlap between the red and the green. Fine, it's just going to do as good as it can. Okay. So that's the algorithm. As I said, published in 1956. If I went ahead and built a computer like this is freaking 1960. This is a long time ago. There's not very many computers in existence in this point. And they did exactly what I just sort of described here, is you have some sort of photosensitive, sort of a bunch of photodetectors that we're going to call our retina. So you can shine light on this thing and it'll cause electrical activity here. We've got a bunch of these association units. These are the things that are pulling out features from the retina space, and these are the things that are sort of going to be randomly connected. And by randomly connected, we do literally mean randomly connected. This diagram over here on the left, that is all right, let's take a bunch of wires from the retina and just randomly plug them in to these other things that are going to be doing interesting random combinations of the data from pulling out sort of random features from the input image. And then beside this, we then have these response units, these things that have electrical connections to all of these feature detectors. And these electrical connections, in order to add up the current like that, that's nice and simple. You can have variable resistors do that, and that's actually exactly what but then you need to have this trainable. You need to have this learned. You need to have that learning process happen. So you need some way of adjusting how strong the electrical connection is between these points, and that's a variable resistor. That's what variable resistors are for. And that's actually what they did. They had like motors that would, so it's back in those days, you've got, potentiometer, or you've got these components that you can adjust the resistance of a wire, and you do that by turning them, by twisting them, and so they just literally mounted motors onto those and had that sort of twist the motor, or twist the variable resistors themselves, implement that learning rule, and now, as long as you've got some sort of training signal, you can go ahead and get this thing to learn whatever you want. You can recognize different letters. You can just recognize different inputs, categorize different inputs in different ways, just by doing this feedback loop. And they physically implemented this learning algorithm in analog hardware. Cool. So that's kind of nifty. What can you do with that? One aspect that's out there, so one aspect that comes up pretty quickly is, well, what if you want a system that can categorize more than one thing? So I have a system, maybe it recognizes cats, it recognizes dogs, it recognizes houses. There's more than one category. How do we want to organize our outputs? Because the way I've described things, each output is either yes or no. Some things that people played with was, okay, maybe you could have one thing that says, is it a cat, or is it more like a cat, or is it more like a dog? Another one says, is it more like a dog, or is it more like a house? Another one says, is it more like a cat? You could do something like that. The difficulty is that gets really ambiguous in terms of there's going to be some inputs. If you set up a system like that, it doesn't scale very well because there's lots and lots of cross comparisons. And you end up having this ambiguous sort of thing where you could very easily have it indicate that something is, you can very easily get inconsistent answers, sort of seen in that diagram. So instead, it's much more common to sort of have these outputs be, is it a cat or is it not a cat? Is it a dog or is it not a dog? Is it a house or is it not a house? And that's sort of each of those outputs is doing a separate comparison of that type. Cool. So we have these perceptrons. There's great excitement. Look, we can get neurons to go ahead and do things. So that was 1956, 1960. We got this machine. People are building machines to do this. This is really, really cool. 1969 comes along, and this book, Minsky and Papert Perceptrons, comes out. This is the book that is often cited as the book that destroys neural networks for 20 years and just kills the whole thing, just kills all of this excitement. It's just like where people are building machines, they're getting stuff that's learning stuff. And figuring out exactly why this book killed off neural networks for a while is a little bit tricky. Perceptrons is often also cited as one of these books where lots of people have heard of the book, but very few people have read it. I managed to find a copy at a used bookstore like 15 years ago, and I was so incredibly excited. But anyway, it's got some beautiful quotes in it. And I think, interestingly, a lot of the quotes, I think, ring true now to a lot of the sorts of questions people have about neural networks in general. So I've got a couple sort of extended excerpts here. But you get quotes kind of like this. Our discussion will include some rather sharp criticisms of earlier work in this area. Perceptrons have been widely publicized as pattern recognition or learning machines, and as such have been discussed in a large number of books, journal articles, and voluminous reports. The quotes on reports there is just hysterical. Anyway, most of this writing, some exceptions are mentioned in our bibliography, is without scientific value, and we will not usually refer by name to the work we criticize. That's just stunning. Like I cannot imagine writing something like that. But anyway, yeah, most of this writing is without scientific value. All right, so what are they talking about here? The seductive aspects of perceptrons. The purest vision of the perceptron as a pattern recognizing device is the following. The machine is built with a fixed set of computing elements for the partial functions, the features that we're extracting, usually obtained by a random process. To make it recognize a particular pattern, a set of input figures, one merely has to set the coefficients alpha, that's our connection weights, to suitable values. Thus, programming takes on a pleasingly homogeneous form. Moreover, since programs are representable as points in an n-dimensional space, that's the space of possible connection weights, they inherit a metric, which makes it easy to imagine some kind of automatic programming which people have been tempted to call learning. By attaching feedback devices to the parameter controls, they propose to program the machine by providing it with a sequence of input patterns and an error signal, which will cause the coefficients to change in the right direction when the machine makes an inappropriate decision. The Perceptron convergence theorems define conditions under which this procedure is guaranteed to find, eventually, a correct set of values. So that's exactly okay, you're going to be setting up some connection weights, you're going to do some sort of learning rule, and I love that Minsky and Papert are unwilling to just accept calling that learning. They just want to look, all it is some really dumb algorithm that says just adjust these weights based on this error signal. And they want to resist calling that learning, which is, I think, an interesting distinction to make. Because it's certainly not the sort of rich sort of learning of how the term might be used when talking about people learning or animal learning or things like that. In any case, so then say, all right, to separate reality from wishful thinking, again, beautiful lines, we begin by making a number of observations. And then they go into various things about the critiques of perceptrons. Now, the thing that's often cited about their critique is that a perceptron cannot compute the XOR function. And this is the diagram that I sort of showed before and sort of mentioned before, that if you have features, if you have, say, an input that is like this, where, hey, I would really like an output, so I have two inputs, and I would really like the output to be a 1 if either of the two inputs is 1, but not if both or neither of them are 1. Okay, that's something that is generally commented that the perceptron cannot do. That's not quite technically true. The perceptron's perfectly fine at computing XOR. And that's because the perceptron is defined as not just this decision-making system, it's features plus this decision-making system. Okay? We can compute the XOR if we had the right set of features. Okay? Yes, if the output from our features was such that, hey, I need to make my decision based on this feature has to be a 1, or this feature has to be a 1, but not both, and not neither. That we can't do. But if my raw input is just ones and zeros, and I have a bunch is of that form, and I have a bunch of features, then I can go ahead and use a different set of features, and then it's perfectly easy to compute that that XOR function across this whole system. Okay. As long as you've got the right features, any functions will be computed. Right. And that was extremely well known. Like in the original very first paper with perceptrons, everyone, that was very clear and very talked about, and that was the whole point. So that's not actually the problem that's being pointed out in the Perceptrons book. The bigger problem, and the thing that they've spent a lot of time focused on, is where the heck do you get these input features? There was no theory at all for the learning of these input features. There's beautiful theory, beautiful proofs for the learning of this stuff over here. Nothing for how do you get where these features come from. How many of them do you need? And then they had a whole bunch of nice sections in this paper showing that for a whole bunch of interesting computations that you might want to do, you start needing exponentially many features in order to go ahead and compute that. Another big thing that they focused on is what the heck the magnitude of the weights that you need across here. So you very quickly get some situations where like some of your weights need to be minus 0.00003 and other weights are 12 million and 2. And so you just, and that's really difficult to implement in hardware. Also, if you get sort of extreme values, it's going to be difficult to implement in software as well. And all of these proofs for how that, yes, you can eventually learn things, had hit a whole bunch of practical problems of, well, how long is learning going to take? That's the core thing that this book, Perceptrons, Minsky and Papert, 1969, that's what they were focusing on, and those were the problems that killed neural networks for about 20 years or so. That said, okay, yes, we can build these things. We've got some gorgeous proofs for some aspects of the learning, but only if you've got the right features, only if you've got the right data being extracted out. Cool. All right. So that's getting us started into the very sort of first steps of building up artificial neural networks. As I said, there's no required reading. Those original papers I've posted them just because they're fascinating. I find them fascinating. Go ahead and read those because those give a nice background. The Minsky and Papert book is also available if people really want it. I can get a hold of that. But the sort of project ideas, there'd be a bunch of fun things in this, even just on this, is sort of things like, well, the Minsky and Papert book point out a whole bunch of strange tasks that are really, really hard to do with the sort of the classic perceptrons, and those could be a very interesting things to compare on sort of the modern large neural network stuff that that we'll talk about later in the course. Also might be just kind of interesting, the Mark I Perceptron paper has a bunch of examples of things that it was able to do, and in the user manual, and even just sort of a classic recreation of that sort of thing. It would be a fun project. Cool, but that's perceptrons. Our next lecture is going to go on to an alternate way of thinking about how we get those output connection weights, or how that learning process for the perceptrons, and then that's going to lead us fairly natural into the thing that fixes all of this, and has the new revival of neural networks that happened in the 80s, and that'll be the lecture after that. Okay, see you later.